Hi, welcome back. We're going to continue our discussion with dealing with functions of multiple variables. Today we're going to talk about those cylindrical coordinates. We have studied this in the past years when we talked about converting rectangular coordinates. Remember, that's those equations dealing with xy coordinates, and we converted them into polar equations, or r comma theta. We do this because it's sometimes easier to represent functions and do calculus with polar functions than rectangular systems. Today we're going to extend the two-dimensional into a three-dimension system. And in 3 dimensions, we call them cylindrical coordinates. So these are very similar to what we did for years to polars. And even you'll see the conversion process are the same. In a cylindrical coordinate system, the point P in space is represented by the order triplet R, theta, z. So in rectangular, it's using x, y, and z. Now notice they both share the same z value right there. So that's going to be kind of important for us right there. So, all right, let me go and erase that. Z, now the only difference is z is a directed distance from r theta to p. In other words, it's just the from the xy plane. If you look at the x, the y plane, if we have a point here that we have r theta, we have to go up to some point z, some height z right there. Our conversion to get x is r cosine theta, y is r sine theta. Notice this is just from polars, and our z coordinate just remains the same. Going backwards, to go from rectangular to cylindrical, again, we have r squared equals x squared plus y squared, and tangent theta equals y over z. Again, we got this from polars, from pre-cal. So let's just practice converting. Now, just like in polars, we call the point 0, 0, 0 the pole. So we want to convert the following point, r theta z, into rectangular coordinates. So that's not too hard to do. Well, to get x, it's just going to become r, which is 4 cosine 5 pi over 6. Y equals r, which is 4 sine 5 pi over 6. And, of course, z is just going to be 3. So if we simplify this, of course, this becomes 4 cosine of 5 pi over 6 is negative root 3 over 2. So my x coordinate will be negative 2 root 3. My y coordinate, this becomes 4 sine of 5 pi over 6 is just positive 1/2. So my y coordinate is 2 and z is just 3. Again, the first two coordinates for here is just from polars. So let's convert the point xyz into a cylindrical coordinate. Well, now we're going to use a little formula right here. So what do we need? We need r. Well, to get r, it's just the square root of x squared plus y squared. So r is going to become the square root of 1 plus 3 squared is root 3 squared is 3. So we get 2. Theta, we're going to use tangent. So we know that the tangent of theta is, my rule says y over x, so y over x, which is root 3 over 1. So theta is, of course, that inverse tangent. So then we get two answers, pi over 3 and 4 pi over 3. Now notice we do get two answers. And the reason we get two answers is that this is a cylinder. So we're going to get two answers here in this case. And, of course, z is just 2. So to get our answers, to get our points right here, we're going to get our first one, r, which is going to be 2, theta, pi over 3, and then z is also 2. Now, we actually do get another point. So we also have to deal with the 4 pi over 3. We get 4 pi over 3, and z is still 2. But remember, we're looking at the angle here. If we look at a right triangle, if we look at our graph right here, x, y, z, right here, of course, 2 pi over 3, 2 is over here. But when we go to 4 pi over 3, that becomes over here. Notice over at this point, x is less than 0. So my x-coordinate here becomes negative 2 because we're at 4 pi over 3. X is negative. So we have I should say that. X is negative at 4 pi over 3. So that's going to give me a negative value right there. That's kind of a tricky question right there. Now, why do we like cylindrical coordinates? Well, for one, cylindrical coordinates are very useful at representing cylindrical surfaces. So basically anything that has kind of like a round surface. I kind of drew like a little cylinder right over here. And for surfaces of revolution with a symmetry about the x-axis. When we get to areas and volumes, we're going to be talking about this later on this year. In other words, so imagine we have the cylinder. Ready? X squared plus y squared equals 9. Now we know that x squared plus y squared equals 9 is a cylinder in 3D. In 3 dimensions. Well, we have x and y coordinates. Well, in cylindrical form, I could rewrite this in cylindrical, there we go, form. I could rewrite this much easier. We know that x squared plus y squared equals r squared. So therefore, my cylinder could just be written as r squared equals 9 or r equals 3. And this is a lot easier to work with when we have to start doing the calculus on these later on. All right, go to part 2, and we're going to work on how to convert some other formulas on these, okay? Hope to see you then. Bye.